गुड इवनिंग एवरीवन। आज हम एनसीईआरटी क्लास 11 के एक बहुत ही सिग्निफिकेंट चैप्टर डिस्ट्रीब्यूशन ऑफ ओशंस एंड कंटिनेंट्स को डिटेल में एनालिसिस करेंगे। स्पेशली केवीएस एनवीएस जैसे इंटरव्यू में आपको कैसे कंसेप्चुअल और एनालिटिकल आंसर्स प्रेजेंट करना है, वो ही आज हमारा मेन फोकस है। सो लेट गेट स्टार्टेड। So the first question, if the panel ask that what was the fundamental premise of Alfred Wegener's continental drift theory? So we can answer like this. Alfred Wegener proposed that all continents once formed one single continental mass that was called the Pangea, and that was surrounded by uh, surrounded by a mega ocean called the Panthalassa. About 200 million years ago, Pangea began to split. Example like a jigsaw puzzle that was once whole but later separated into individual pieces. So the next question, if you mentioned jigsaw feet, where is the evidence most striking? If the question number 2 is like this, so we can answer like this. The most remarkable feat is between the shoreline of South America and Africa. The bulge of Brazil is perfectly into the Gulf of Vienna. It is matching the torn edges of two pieces of the same, just like a newspaper. Okay. So if the next question is asked like this, how do the placer deposits support the theory of continental drift? So what is placer deposits? Okay. So the placer deposit, uh, uh, just like gold placer deposits occurred on the Ghana coast, Africa, but the source rock is found in Brazil, in South America. Since there are no source rocks in Ghana, it provides the continents was once joined together. For example, it's like finding a specific gold coin in one room, but the treasure chest it belongs to in the room the next door. So the next question, what role the tillite play providing the existing Gondwana land? So we can answer like this. Just wait for a while. So the next question is, what role does the tillite play in providing the existence of Gondwana land? So tillite is sedimentary rock formed by glacial deposits. Identical glacial tilites are found in India, Australia, Falkland, Madagascar, Antarctica. These landmasses shared a common geological history. For example, like finding the same rare ancient ice sculpture tool in 6 different distinct houses. So the next question is Wegener cited about polar fleeing force. Why was this criticized by later scientists? If the next question asked like this about the polar fleeing force, so the polar fleeing force, why does it was criticized? The Wegener suggested that the centrifugal force of Earth rotation caused the drift. However, most scientists found this force was too weak to move a massive continent. For example, it's like trying to push a heavy truck by simply blowing air at it. The force is inadequate for the mass. So the next question, how did Arthur Holmes refine the understanding of what moves the continents? So Arthur Holmes, we learn about the theory of Arthur Holmes, convective current theory. Convectional current theory. So in the 1930s, Holmes proposed the convection current theory. He argued that the thermal energy from radioactive elements in the mantle, the thermal energy of radioactive elements in the mantle creates a convective cells that drive crustal movement. For example, like the circular movement of boiling water in a pot that shifts the lid upward. So the next question, the post-war ocean floor mapping revealed something unique about the mid-oceanic ridges. What was it? So now we'll learn about the mid-oceanic ridges. Okay. So the post-war ocean floor mapping revealed something unique about the mid-oceanic ridges. What was it? Mapping revealed that the mid-oceanic ridges are the most active volcanic regions, and that the rock near the crest are remarkably young compared to those that are farther away. So these rocks near to the uh, just near to the crest is youngest, and compared to those farther away. Next question, explain the seafloor spreading hypothesis by Harry Hess. So now we learn about the seafloor spreading. Harry Hess argued that the continent eruption at the crest, this is the crest of oceanic ridges, cause ocean floor to split and spread. New lava from this region pushes the older floor away, like a conveyor belt at an airport that continuously brings out the new luggage, moving the old ones forward. Next question, if the seafloor is spreading, why it is not it isn't the earth's total size increasing? So we can answer like this: while the new crust is created at the ridges, while the new crust is created at the ridges, the old crust is simultaneously being consumed or destroyed at the oceanic trenches through a process called subduction. For example, it works like a treadmill where the belt comes out from one end and disappears into the other. So the next question, how does paleomagnetism confirm the theory of seafloor spreading? Now we learn about the paleomagnetism theory. What is the relationship between paleomagnetism and seafloor spreading? Okay. Okay. Now we learn about the paleomagnetism. So paleomagnetism, what is paleomagnetism? The rocks on either side of ridge, show matching pattern. There is a matching. Okay, reveals that reverse polarity at equidistant intervals. For example, like a mirror image. This is the mirror image of that one, and that is the mirror image of this one. So, like a mirror image where the pattern on the left perfectly matches the pattern on the right. So, next question. Moving to plate tectonic. How is the plate defined in this context? So what is the plate? Our next concept is what is plate? Okay. So a tectonic plate, also called lithospheric plate, is a massive, and irregularly shaped slab of solid rock. That is slab of solid rock composed of both continental and oceanic lithosphere. So the next question is, what is the difference between convergent and divergent plate boundary? Okay. Okay. So a divergent plate boundary A divergent plate boundary, plates pull away. Plates pull away. In case of divergent plate boundary, for example, the mid-oceanic ridges or mid-Atlantic ridge. At a convergent boundary, one plate subducts under another, forming trenches or mountains. For example, Himalayas. Next question, can you name a specific transform boundary? So now we learn about the transform boundary, what is transform boundary and examples of transform boundary. So in case of transform boundary, the one most important example of transform boundary is the San Andreas Fault in California. Here plates slide horizontally past each other. So crust is neither produced nor destroyed. For example, like two cars brushing past each other in opposite direction on a narrow road. So the next question, what determines the rate of plate movement? So the rate of plate movement greatly the the rate of movement vary greatly. The Arctic region has the slowest rate, that is 2.5 centimeter per year, while the East Pacific rise that has the fastest more than 15 centimeter per year. So the next question is the how did the Indian plate move to its current position? So the India was a large island in the southern hemisphere. Okay, it moved north, crossed the equator, and okay. So the India was a large island and was in southern hemisphere. It moved north, crossed the equator, and eventually collided with the Eurasian plate about 40 to 50 million years ago. So next question, what is the role of Tethys Sea during the collision? So now we learn about the Tethys Sea and its importance. So as India moved northward, the Tethys Sea flowed subducted. The Tethys Sea flowed subducted under Asia. The sedimentary deposits of the Tethys were later uplifted to form the Himalayas, like a rug being pushed against a wall, causing to fold and rise. So the next question, why are earthquakes and volcanoes concentrated along the plate boundaries? So the next question, why are earthquakes and volcanoes concentrated along the plate boundaries? These boundaries, these boundaries are zones of intense friction, melting and pressure release. The interaction between the rigid plates causes the release of energy. So the next question, what is slab pull in the context of plate motion? So the slab pull is a force where the cold dense edge of a subducting plate sink into the mantle and pulls the rest of the plate behind it, and pulls this portion, pulls this that portion. Okay, so this slab pull is the force where the cold, this is the cold and dense edge of subducting plates sink into the mantle and pulls the rest of the plate behind it, like a heavy weight towel falling off a rack. The weight of the hanging part pulls this part, the weight of this part just pulls the rest down. So next question, how do hotspots provide evidence for plate movement? So what is the evidence of hotspot? So what is the question? How do hotspot provide evidence for plate movement? So hotspot remain stationary while the plate this the hotspot. Okay, the hotspot remains stationary while the plate moves over them. These are the plate. This moves. These plates are moving, and this is in stationary state, creating a chain of volcanoes. For example, like moving a piece of paper over a fixed candle. These are piece of paper and this is the fixed candle. Okay, creating a line of scorched spots. Okay. Next question. As a geographer, why is this chapter vital for understanding the earth? So this chapter, the distribution of oceans and continents, provides a grand unified theory of geology, explaining everything from the origin of mountain to the location of earthquakes and the evolution of current map. So thank you for listening. This is for today. Keep listening for further videos. Thank you.